right now there are these multi-million-dollar drill rigs boring deep into the Earth's crust.
Oh, yeah. Massive machines.
Massive, and literally the only thing stopping them from instantly welding themselves into a useless hunk of scrap metal is, well, a millimeter-thin layer of bright red sludge.
It's kind of wild to think about.
It really is. So welcome to today's deep dive. Our mission for you, the listener, is to extract the hidden high-stakes reality from what honestly initially looks like an incredibly dry technical document.
Right. The source material today is a product data sheet.
Yeah, for JET-RED premium multipurpose grease, which is manufactured by JetLube. And the visual presentation of this document tells a very specific story before you even read a single specification.
It really does set a mood.
It does. It's filled with these gritty, high-contrast black and white photos, massive oil rigs, towering stacks of heavy construction pipes, workers silhouetted against these freezing, snowy landscapes.
Right. It's all heavy metal and harsh environments.
Exactly. But smack in the middle of this stark, gray imagery is a bright, glossy, candy apple red tube of smooth grease. The visual contrast is just, it's jarring.
It immediately forces your attention to scale, I think. You have this unforgiving, monumental mass of industrial machinery in the background.
Right.
And it's contrasting with this relatively small, highly engineered chemical compound in the foreground that, makes all of that heavy lifting possible.
Okay, let's unpack this, because looking at this contrast, I immediately thought of the human body.
Oh, interesting. How so?
Well, if the massive steel I-beams and the drilling rigs are the bones of our civilization, like those heavy structural elements, then this bright red grease has to be the vital cartilage.
That's a good way to look at it.
Right. It's the invisible microscopic padding keeping the whole world from just grinding to a screeching halt. So is it fair to call this red sludge the ultimate armor for modern civilization?
Well, what's fascinating here is that the cartilage analogy works, but we really need to look at the mechanics of why that armor is necessary in the first place.
Okay, break that down for me.
So you were dealing with multi-ton pieces of equipment.
Yeah.
Right? Things operating in deep earth mining or heavy ship.
We do see that.
Exactly.
Yeah.
If you have two steel surfaces under that much load moving against each other, the kinetic energy generates immense heat.
Just from the raw friction.
Right. And without a highly specialized boundary layer like this jet-red grease, the metal doesn't just scrape. It actually begins to microscopically melt and fuse.
Wow.
Yeah, the machine literally consumes itself. So calling it armor is mechanically accurate. It is a chemical shield designed to sacrifice itself so the steel doesn't have to.
That is intense. And the data sheet actually breaks down the anatomy of the specific shield. It classifies JET-RED as a high-temperature lithium complex grease.
Right.
And it notes the base fluid is petroleum oil. But for anyone who assumes grease is just, thick oil, there's clearly a structural difference here. What is the lithium complex actually doing?
So, to understand the engineering, you have to think of the lithium complex not as a liquid, but as a microscopic three-dimensional sponge.
A sponge.
Yeah, a highly stable crystalline matrix. The petroleum oil is the actual lubricating agent, but oil by itself is just a fluid.
Yeah.
It naturally wants to flow away from pressure.
Right. It just squishes out of the way.
Exactly. So the lithium complex matrix traps the oil. When a heavy bearing rolls over this grease, the pressure physically squeezes the sponge, forcing the oil out to lubricate the metal.
Oh, that makes sense.
And then the moment the bearing passes and the pressure drops, the matrix expands and sucks the oil right back in.
That's a brilliant mechanism. The thickener is really just the delivery system for the oil, releasing it exactly when and where the kinetic force demands it.
You nailed it.
And the data sheet points out that its primary function is to protect specific components like bearings, journals, and moving parts from environmental contaminants. Dirt, dust, high humidity, rain, snow.
Which is exactly why the physical architecture of the grease is engineered so tightly. The document mentions its high film strength. That means the molecular bonds of the oil and the thickener actively resist being severed or pushed aside by sheer mechanical force.
And simultaneously, it's formulated to be pumpable.
Yes, very important.
Because in a massive industrial plant, grease isn't always applied by hand, right? It's pumped through hundreds of feet of narrow tubing to reach enclosed bearings deep inside machinery.
Exactly. But, I think we should look at the texture.
Yeah, actually, I am looking at the typical characteristics chart right now, and I want to push back on the specific wording they use to describe the texture of this grease.
Okay, what stood out to you?
It says the texture is smooth/tacky.
Right, smooth and tacky.
Wait, smooth and tacky. How can a lubricant be smooth and tacky at the same time? If the entire goal of this chemical armor is to prevent friction, shouldn't it be as slippery as humanly possible?
You think so, yeah.
Deliberately making it sticky feels like you are introducing drag into a system you are trying to make efficient.
It definitely seems counterintuitive until you factor in the physical forces at play inside, say, a turbine or a high-speed blower.
Okay.
The datasheet specifically notes this grease can handle DN speeds up to 200,000.
Which is, what does DN speed mean?
DN is a factor of the bearing bore size multiplied by the RPMs. So to visualize that, imagine the internal steel components of a machine whipping around with thousands of G-forces of centrifugal energy.
That's a massive amount of spin.
Huge.
Yeah.
If the grease were only perfectly smooth and slippery, that rotational force would instantly fling the lubricant right off the metal and onto the walls of the housing.
Oh, I see. Leaving the bearing completely dry.
Exactly.
So the tackiness is an adhesive requirement. It's like a rock climber who needs incredibly sticky rubber shoes to cling to a vertical wall, but still needs to move fluidly up the rock face.
That's a great visual.
The tackiness anchors the grease to the metal.
The climber analogy works well for the static adherence, but mechanically imagine a deck of cards.
Okay, a deck of cards.
If you press your hand flat on top of the deck and slide it forward, the bottom card sticks to the table, the top card sticks to your hand, but all the cards in the middle slide past one another.
Oh, right, they fan out.
Yeah, that is how shear works in a tacky grease. The tacky quality ensures the bottom and top layers adhere violently to the metal surfaces.
While the smooth quality allows the internal layers to just slide.
Right, the internal layers of the petroleum oil shear and slide against themselves with minimal resistance.
That's so clever.
And furthermore, that sticky adherence forms a physical gasket around the bearing, sealing out the dirt and the oxygen, which stops rust before it can even initiate.
Here's where it gets really interesting, because the datasheet doesn't just state that the grease is tough. It lists the specific ASTM laboratory tests used to prove it.
And these are not easy tests.
No, they're grueling standardized trials. For example, the ASTM D92 test for the flashpoint shows all grades of this jet-red grease survive over 430 degrees Fahrenheit.
Which is about 221 degrees Celsius.
Yeah. Right, without igniting. But the metric that really caught my eye is the ASTM D2596 test, the 4-ball weld point. The result listed is 500 kilograms.
Ah, yes. The 4-ball test is one of the most brutal environments you can subject a chemical to.
How does it work?
They lock 3 steel balls together in a triangle, place a 4th spinning ball on top of them, coat them in the grease, and then just apply downward force.
And 500 kilograms of force is half a metric ton.
Yes, it's immense.
So they are pressing half a ton of weight down onto these small metal spheres just to see at what point the friction heat spikes so high that the metal spheres completely fuse and weld themselves together.
Exactly.
I mean, this sounds like a medieval jousting tournament for physics. I'm struggling to understand the physics here, honestly. How does a microscopic layer of oil and lithium sponge survive half a ton of crush weight?
It's hard to wrap your head around.
Wouldn't the pressure just instantly squeeze every drop of liquid out of the way, resulting in bare metal-on-metal contact?
If we connect this to the bigger picture, you are hitting on the exact limitation of standard oils. Under half a ton of pinpoint pressure, standard oil does get squeezed out. The boundary layer collapses entirely.
So how does Jet-Red survive it?
Well, to score a 500 kilogram weld point, you have to engineer the grease with extreme pressure, or EP additives.
Okay, EP additives.
The datasheet doesn't list the exact proprietary chemical breakdown, but generally EP additives involve sulfur or phosphorus compounds suspended right there in the grease.
So the additives just sit dormant until the pressure hits?
Precisely.
Yeah.
As the pressure builds toward that 500 kilogram mark, the sheer mechanical stress generates intense localized heat.
Right.
That heat triggers a chemical reaction. The EP additives react directly with the steel surface to form a microscopic, solid layer of iron sulfide or iron phosphide.
Wait, really? A solid layer?
Yeah. This sacrificial chemical layer is physically bonded to the metal. Even when liquid oil is squeezed away, this solid additive layer prevents the steel from touching the steel. It takes the absolute brunt of the destructive force.
That completely reframes how I view this document. We aren't just looking at a liquid.
No, not at all.
We are looking at a reactive chemical delivery system that deploys a solid shield exactly when the machine is about to destroy itself.
That's the perfect way to summarize it.
Knowing that, the other tests listed, like the ASTM D4Z48 copper corrosion test, where it scores a perfect 1A, and passing the ASTM D1743 rust prevention test, they make total sense.
They absolutely do.
You have this reactive chemistry fighting off half a ton of crush force on one side, while simultaneously repelling moisture and oxygen on the other.
It is a dynamic chemical environment, and the formulation has to be incredibly stable.
Why is that?
So that the EP additives, the ones meant to react with the steel under pressure, don't prematurely react with sensitive metals like copper or brass and cause corrosion.
Oh, I see.
Achieving a 1A copper corrosion rating means the grease is aggressive enough to stop a 500-kilogram weld, but inert enough not to eat away at delicate bushings.
That's a tightrope walk. But, if this grease is engineered to be this thick, tacky, highly reactive matrix, how does it not cause massive drag when operating in freezing environments?
That's the million-dollar question.
Right. I'd imagine taking a sticky lithium complex into an Alaskan winter would basically turn it into a solid block of glue, bringing the machinery to a complete standstill.
And that is the fundamental thermodynamic challenge of industrial lubrication. A single formulation cannot conquer every temperature extreme.
Okay.
This is why the datasheet introduces 4 distinct grades within the JET-RED product line: EP00, EP0, EP1, and EP2.
And what do those numbers mean?
These represent consistency grades under the NLGI system, which essentially measures the stiffness of the grease.
The EP2 grade is the stiffest, which the document positions for high heat environments.
Right.
It lists something called a dropping point of 500 degrees Fahrenheit for EP2 and 450 degrees for EP1. So what does this all mean?
Well,
When the temperature inside a machine hits 500 degrees, what is physically dropping?
this raises an important question about the phase transitions of complex chemicals. Remember the lithium complex sponge matrix we discussed earlier?
The three-dimensional net holding the oil.
Right. The dropping point is the exact thermal threshold where that crystalline sponge structure melts.
Oh, wow.
It undergoes a phase transition from a semi-solid to a liquid. The matrix just collapses, and the grease literally drips away from the bearing it is supposed to protect.
Hence the dropping point.
Exactly. Once the grease drops, the bearing runs dry, friction spikes exponentially, and the machine fails within minutes.
But the fact that EP2 maintains its structural architecture up to 500 degrees Fahrenheit means it can operate inside massive industrial ovens or high-temp blowers without collapsing.
Spot on.
And the specs back up that resilience. It shows EP2 has an incredibly low water washout rate of only 5%.
Which is remarkably low.
And a mere 1% oil separation rate. Even under extreme heat and heavy water spray, the matrix refuses to let go of the oil.
But obviously you can't pump a matrix that stiff through a frozen pipeline.
Right, which brings us to the opposite end of the spectrum, the EP00 and EP0 grades.
Exactly. These are formulated with a much lower concentration of thickener.
The source explicitly states they are designed for enhanced flow and pumpability in extreme cold.
Because as the temperature drops, the viscosity of the base oil naturally increases. It thickens up.
It gets sludgy.
Yeah. By starting with an ultrafluid EP00 grade, you ensure that even at extreme temperatures, the grease remains fluid enough to circulate.
The service rating for EP00 goes all the way down to negative 30 degrees Fahrenheit.
Or negative 34 Celsius.
Right. But there is a specific detail in the application section for AP00 that I thought was fascinating because it exposes the messy, pragmatic reality of the industrial world.
What's that?
It highlights that this fluid or semi-fluid grease is perfect for leaky gearboxes.
Ah, yes. It is a stark acknowledgement of real-world maintenance economics.
Right. In a perfect theoretical world, if a massive gear housing cracks or blows a seal and starts leaking oil, you shut down the operation.
You disassemble the rig, replace the seal, and refill it.
Exactly. But if you are in the middle of a remote mining operation, shutting down a primary conveyor system might cost tens of thousands of dollars an hour in lost production.
You cannot always afford the downtime.
No.
So the mechanical stopgap is to drain the straight oil, which will just continuously pour out of the broken seal, and replace it with EP00's grease.
Because it operates as a semi-fluid.
Right.
It is just liquid enough to get pulled into the gears and provide that 500-kilogram extreme pressure protection.
Right.
But it has just enough of that lithium thickener in it to prevent it from seeping out through the damaged seals.
It keeps the machine alive and producing until a scheduled maintenance window.
That is just so practical.
Exactly. And this highlights the logistical value of the entire JET-RED product line.
How so?
By offering consistency grades ranging from the semi-fluid EP00 to the stiff, high-heat EP2, an industrial operation can standardize its chemistry.
Oh, I see. They use the same fundamental chemical armor across the board.
Right. The mechanics grab EP00 for the freezing environments or the leaky gearboxes, and they grab EP2 for the high-temperature friction bearings.
All without introducing incompatible chemical bases into their inventory.
Exactly. It streamlines everything.
We started out looking at a highly technical, seemingly dry product data sheet. Just grids of ASTM test codes, NLGI grades, and temperature ranges.
It looks like alphabet soup at first glance.
It really does. But once you actually decode the physics and chemistry behind those numbers, you realize this document isn't just a list of features. It is a meticulously engineered battle plan.
It is a blueprint for surviving the extremes of physics. Every single day inside heavy drive trains, universal joints, and massive industrial fans around the world, this chemistry is fighting a relentless war.
A war against kinetic friction, thermal collapse, and elemental corrosion.
The massive visible feats of engineering are entirely dependent on the microscopic invisible engineering of the lubricants.
Absolutely. So, to you listening, the next time you are stuck in traffic next to a massive road building operation, or you look up and see a towering construction crane moving tons of steel over a city skyline.
Don't just look at the massive metal beam.
Exactly. Think about the invisible, smooth, tacky red armor hiding inside all those critical joints. Think about the microscopic chemical reactions happening in real time.
Silently absorbing half a ton of crush force so the machine doesn't tear itself apart.
And as a quick detail for anyone thoroughly intrigued by the high-stakes engineering of industrial lubricants, the data sheet actually lists the manufacturer's engineering hotline right at the bottom.
Oh, nice Easter egg.
Yeah, it's 800-538-5823, or you can find the technical specs at jetlube.com. It's just a fascinating peek into an industry that operates entirely behind the scenes, keeping the gears of everything moving.
Literally keeping the gears moving.
Literally. So we'll leave you with this final thought to explore on your own. If a simple tube of red grease is engineered with this much hidden complexity, designed to deploy chemical shields under half a ton of pressure and survive 500-degree heat, what other invisible engineering miracles are you walking past every single day without noticing?